All right, let's dive straight into this explainer and tackle a massive engineering puzzle. How do we take a tiny laboratory discovery and blow it up into a massive industrial operation without the whole thing ending in disaster? I mean, it sounds pretty straightforward, right? You mix some chemicals in a small flask, get a great results, and then just do the exact same thing in a giant vat. But as we're about to see, the universe absolutely does not work that way.
We've got a clear roadmap for today with 4 main stops. First, the scale-up challenge. Then, the language of dimensions. Next, dimensional homogeneity. And finally, dimensional analysis in action.
So let's kick things off with Section 1, the Scale-Up Challenge.
It really is a fascinating question. Why can't we simply take a chemical reaction that works perfectly in a little beaker and just build a proportionally giant tank for the factory? Why does scaling up a process present such massive hurdles that can literally ruin an entire production line? To get to the bottom of this, we're drawing directly from some foundational textbook notes shared by the chem_eng_world community. And these texts point out a pretty harsh reality about process engineering. The core issue is that physics fundamentally changes at scale. That means you can only ever achieve what's called partial similarity between the lab and the factory. Direct one-to-one scaling, it just doesn't work. As things get bigger, variables like temperature dependencies or fluid viscosity, especially with those tricky non-Newtonian fluids we see in biotechnology, start behaving totally differently. The standard textbook theories honestly just aren't enough to predict those massive shifts. Which brings us to Section 2, the language of dimensions. To solve this scaling mystery, we first have to learn the grammar of the universe. Every physical quantity is a partnership. It's a strict pairing of a number and a specific measuring unit. You can't just say a mass is 5. I mean, is that 5 kilograms, 5 grams? The number is completely meaningless without its unit.
And that brings us to the 7 base dimensions of the SI system. Think of these as the fundamental alphabet that we use to describe literally everything in the physical world. Whether you're measuring the length of a pipe in meters, the time a reaction takes in seconds, or the temperature in Kelvin, every single physical reality is rooted right here in these core dimensions.
What's brilliant here is understanding the difference between that basic alphabet, like length and time, and our broader vocabulary, which we call derived dimensions. Velocity is a perfect example. You can't measure velocity without referencing both length and time. It's a combination of those basic letters.
Speaking of base dimensions, consider this truly massive number, Avogadro's number. It represents exactly 1 mole of a substance. But you might be wondering, why do engineers even care about this specific quantity when they could just weigh things on a normal scale? Well, chemical engineers use moles instead of raw mass because chemical reactions are fundamentally about individual molecules pairing up. They don't care how heavy they are. If you only measure by mass, you're completely ignoring the actual microscopic dance of the chemical reaction. Let's look at hydrogen and chlorine. Translating mass into moles gives us a perfectly balanced 1-to-1 ratio of reacting molecules, and that is absolutely vital for scaling up recipes. If you tried to scale this up by mass, needing 2 grams of one thing and 71 grams of another feels completely arbitrary. But through the lens of moles, it's a beautifully simple 1-to-1 relationship. Let's move on to Section 3, dimensional homogeneity. Now that we know the vocabulary, we need the unbreakable rules of the game. This quote acts as an absolute law of physics. For an equation to be true everywhere in the universe, the dimensions on both sides of the equal sign have to match perfectly. You can't have an equation that spits out meters on one side and seconds on the other. That is literally trying to say an apple equals an orange. To see how strictly this rule is enforced, let's compare 2 of Newton's incredibly famous laws, the second law of motion and the law of gravitation. Both of these equations are solving for force. But if you look at the components on the right side, they are entirely different. So how on earth can they both result in the exact same dimension of force? Well, in the second law of motion, when you multiply mass by acceleration, you get the derived dimension for force. That's mass times length over time squared. It just naturally balances out perfectly. But the law of gravitation, that doesn't naturally balance to mass times length over time squared. So if an equation doesn't naturally balance out, engineers have to introduce a dimensional constant, like the gravitational constant g or the universal gas constant r. These constants aren't just random numbers. They have a very specific job. They magically fix the grammar of the equation by providing the exact dimensional units needed to make the left side perfectly match the right side.
And that leads us to our final stop, Section 4, Dimensional Analysis in Action.
So that seemingly impossible task of scaling up, it actually becomes completely manageable when you follow this strict two-step mathematical procedure. It is an incredibly structured way to cut right through the chaos of massive industrial processes. Step 1 is compiling a relevance list. This means laying out exactly what you want to find out, your target quantity, and every single physical factor that might influence it. For instance, if you want to understand what dictates the swing of a pendulum, you have to list everything that could possibly matter. The length of the string, the mass of the weight, the downward acceleration from gravity. You need the whole picture.
But here is the catch. To avoid breaking the math, you absolutely must ensure that none of the parameters on your list are just hidden, derived versions of each other. They have to be primarily independent. If you include parameters that are basically measuring the exact same underlying physical reality, your whole analysis will just fall apart.
Once your list is set, you hit step 2. You have to ask this critical question. Can this physical content be formulated in a dimensionally homogeneous manner? It's a stress test to ensure your scale-up won't literally violate the laws of physics. If your parameters can't be arranged to perfectly balance the dimensions, you are definitely missing something fundamental on your relevance list.
And this brings us to the ultimate trick of the chemical engineer. By carefully combining those physical parameters, engineers convert complex variables into dimensionless numbers. Because these numbers have 0 physical units attached to them, the units have all canceled each other out, they act as a universal translation key. A dimensionless number behaves exactly the same way in a tiny 1-liter beaker as it does in a massive 10,000-liter industrial reactor. It's brilliant.
By understanding the fundamental language of dimensions and forcing our math to obey the rules of homogeneity, we completely unlock the ability to scale up modern industry. It really leaves you wondering, how many other seemingly impossible translation problems in our world could be solved if we just applied this universal language of dimensions? Thanks for joining me on this explainer, and I'll catch you in the next one.